Section 2.6, Continuity. Chapter 2, Limits. Let's begin with our definition of continuity at a point. A function f is continuous at a point as the limit approaching a of f of x equals f of a, and f of a is not a whole or an asymptote. So we're basically saying that the limit is the function is continuous if it's possible to evaluate at that limit. Now let's go ahead and go through our continuity checklist. In order for f to be continuous at a, the following three conditions must hold. First, f of a is defined, meaning I can evaluate for it. It's part of our domain. 2, the limit as x approaching a of f of x exists. And 3, the limit as x approaching a of f of x equals f of a. That is our continuity checklist. Let's do this example. Use a graph of f to identify the values of x on the interval 0 through 7 for which f has continuity. Alright, so I'll look at 0 through 7. So I look at all these values and there's all these holes, all these values where I have to be careful as to whether it's continuous or not. So for that, we have to look at our rules above. Remember, it's part of our domain, it exists, and you can evaluate at that number. So let's look at 1. So looking at 1, it fails that continuity part, right? It's a whole. So we can say something like f of 1 is not defined, meaning we have a whole. Let's take a look at what's going on at 2. So as we look at 2, we see that we have a whole and we have a value, right? So for f of 2, we can say, well, f of 2, we have a value for it. It is 3. And the limit as x is approaching 2 of f of x, well, our function altogether seems to be approaching 1, where the whole is. Thus, f of 2 and the limit as x is approaching 2 of f of x exist, but are not equal. All right, next we have 3. So if we look at 3, there is a break. So we see that the limit from the left side does not equal the limit from the right side. So for 3, we can say something like, the limit as x is approaching 3 of our function does not exist. Because, well, the right-hand limit and the left-hand limit are not equal. So the limit as x is approaching 3 from the left of your function is not the same as the limits approaching from the right of your function. All right. And for 5, we see we have an asymptote, right? We have an asymptote going on there. So we'd say that neither the limit exists, so as limits approaching, as x approaching 5 of f of x, nor the function is possibly evaluated at that value. So none of them exist. Let's go ahead and take a look at an example. Determine whether the following functions are continuous at a. Justify each answer using the continuity checklist. Okay, so I can't evaluate at that. And it's, if you look at our numerator, can we factor it? What number multiply give us 3, multiply give us 3, that to give us 2. Nope, it's not factorable. So you want to evaluate at A, and your numerator is not factorable. So we have a problem, because at the value for which you're trying to evaluate 1, that is a part that's not defined in our domain. It's an asymptote. So we have an asymptote, so that's a problem. And also, the function f is not continuous at 1. The function f is not continuous at 1 because f of 1 is undefined. So for this one, it's not continuous, and these are our main reasons why. Let's go on to our next example, B. So we have g of x equals 3x squared plus 2x plus 1 divided by x minus 1, and I want to see if it's considered continuous at x equals 2. Well, it doesn't give us a problem in the denominator, right? I can plug in 2 for the denominator, and we don't get an undefined value. It won't give us an asymptote. Okay, so we can just go ahead and plug it in. 3 times 2 squared plus 2 times 2 plus 1 divided by 2 minus 1. Once you work it out, take your time, you get 17 over 1, which is just 17. So yeah, it's continuous. So G is continuous at 2 because the limit as x is approaching 2 of g of x equals g of 2, which is just 17. Let's take a look at our next function. So we have a piecewise function at sine of x equals, no, x sine of x. I keep saying that wrong. So your function is x sine of 1 over x and 0. For x sine of 1 over x, x can't be 0. And for a function 0, x equals 0. And I want to test that value to see if it's continuous at 0. Okay, well, if I look at my function, we have, if I plug in 0, I get 0, right? So the limit as x approaching 0 of your function h of x, so this should have been h of x, equals, it's evaluatable. I don't know if that's a word. I can evaluate at 0. That's better. Which implies that h is continuous at 0. At 0. Plus, also, I don't know if you might remember, we actually found the limit as x is approaching 0 for this function back maybe in section 1.1 or 1.2. We used the squeeze theorem. So I don't know if you remember, but recall by the squeeze theorem, the limit as x is approaching 0 of x sine of 1 over x, we saw that equaled 0. And we did that one in the past by squeeze theorem. Common continuity rules. If f and g are continuous at A, then the following functions are also continuous in A. Assume c is a constant and n is greater than 0, is an integer. So we have the functions for f plus g, f minus g, a constant times f, so c times f times g, f divided by g, and f of x raised to a power n. Theorem: polynomial rational functions. A polynomial function is continuous for all x, and b, a rational function of the form p over q, where p and q are polynomials, is continuous for all of x for which q of x does not equal 0. Alright, so we've talked about how polynomials are just continuous functions. Think back to your algebra days, we had a graph of polynomial. Alright, so let's take a look at this first example. For what values of x is the function f of x equals 6x over x squared plus 5x plus 6 continuous? Well, let's go ahead and factor. So we're able to factor our denominator. So what numbers? Multiply give me 6, not to give me 5, 3 and 2. So that I have 6x. In my denominator I have x minus 3 and x minus 4. Now we want to find where is it continuous. Well, we have a rational function and it would not be continuous at our asymptotes, right? So it would be discontinuous. We would have a break at those values which make our asymptote 0. So we have x minus 3 equals 0 and x minus 4 equals 0. We get x is equal to 3 and x equals to 4. And those are the values for which we have some type of discontinuity. There are asymptotes. Okay, so then we can come to the conclusion and say, therefore, f is continuous for all x, except x equals 3 and x equals 4. Theorem: continuity of composite functions at a point. If g is continuous at a point f at a and f is continuous at g of a, then the composite function f composed of g is continuous at a. So here we see our theorem 2.1. We see that if g is continuous and f is continuous at that value, then I can hold that limit continuity for that function within. Same thing for 2. If the limit as x approaching a of g of x equals L and f is continuous at L, then we can say that the limit as x approaching a of f of g of x is equal to f of the limit of x is approaching a of g of x. Let's do an example. So we're being asked to evaluate the following function. So the limit as x approaching -1 of the square root of 2x squared minus 1. Alright, so let's go ahead and input a -1 for the inside. We can take the limit of the inside. So if this is like your function g, so g of 1 is equal to 2 times -1 squared minus 1. So we get 2 minus 1, which is just 1. Alright, and we'll be fine because the square root of 1 is defined. So then we can say that yes, it is continuous. Next one. The limit as x approaching 2 of cosine of x squared minus 4 divided by x minus 2. Okay, so let's disregard the cosine and work with our inner function, just like we did before. So let's try to take the limit as x is approaching 2 of x squared minus 4 and x minus 2 divided by x minus 2. So I can factor the numerator. We have difference of squares, which gives us x plus 2, x minus 2 divided by x minus 2 for the limit as x is approaching 2. So my denominator and my numerator simplify so that we have x plus 2. And so we have the limit as x is approaching 2 of x plus 2, we get 4. Right? So let's go back to our problem. We have cosine of x squared minus 4, x minus 2. But we know that inside our parentheses, if I take the limit, we just get 4. So now we're just left to work with the cosine of 4, which you punch into your calculator. It gives you negative 0.654. Let's continue with the next equation, continuity at endpoints. A function f is continuous from the right, or right continuous, at a if the limit as x approaching a from the right of f of x equals f of a. And f is continuous from the left, or left continuous at b, if the limit as x approaching b with a negative of f of x equals f of b. Continuity on an interval. A function f is continuous on an interval I if it is continuous at all points I. If I contains endpoints, continuity in I means continuous from the right or left at the endpoint. So let's go ahead and take a look at an example. So I'm looking at this piecewise function, and I don't know if you want to graph it. Let's go ahead and do a quick sketch. So I know this first one is a parabola, and this bottom one is a line. So if I do a quick sketch, I know that parabola is shifted up one. It's shifted up one, and 0 is included, and only 0 and numbers are less than 0. So it's this. For my other graph, I have a line, have a y-intercept at 5, and I have an open circle. A y-intercept at 5, and it has a positive slope, so it goes that way. Those are really super rough sketches of our graph. Okay, so I want to determine the continuity for this function. All right, so we need to know that this function f is continuous at 0 because it's evaluated at that point, right? Well, the negative continuity, the left continuity. So f is continuous at 0 if I look at it from the left. So the limit as x approaching 0 from the left of our function would be evaluated at x squared plus 1 would give us 1. However, if I look at it from the right, the limit as x approaching 0 from the right of your function, which would be the limit as x approaching 0 from 3x plus 5. Well, that is 5, but I cannot evaluate at 0 at that point for our function. It's not contained in our argument. Thus, not right continuous. So then we can say something that our function f is continuous from negative infinity to 0 and on 0 to infinity. Theorem 2.12, continuity of function with roots. So think radicals, so square roots, cube roots. Assume n is a positive integer. If n is an odd number, then f of x equals 1 over n is continuous at all points at which f is continuous. If n is even, then f of x raised to the 1nth power is continuous for all points a for which f is continuous, and f of a is greater than 0. Okay, so we're looking at odds and evens. So why are we taking a look at odds and evens? Well, just so you don't get lost in the wording. If I have something raised to the 1nth power, that means the nth root of that number. So if I have like a is to the 1/2 power, that's the square root of a. If a is raised to the 1/3 power, it's the cube root of a. And we have different conditions for the arguments. I can only take the square root of a positive number, but if I have a cube root, it doesn't matter if it's positive or negative. That's fine. So odd roots allow for negatives. They're okay. Even roots, you only want positives. So that's why you have this argument that f of a needs to be greater than 0, needs to be positive. All right, let's take a look at these examples. For what values of x are the following functions continuous? So for the first one, we have f of x equals the square root of a minus x squared. This graph right here is a semicircle, a top semicircle. Your graph looks like this. All right, so it's continuous along the values that make our argument true. So from -3 to 3. Anything bigger than that will give us a negative argument in our radical. So we can say that it's continuous on -3 to 3. Okay, let's take a look at g of x. So based on my theorem, let's take a look back. I had to be careful with a because I had an even index. I had an even n for f of x to the 1nth power, meaning I need to be careful for when my argument is producing an outcome that's greater than 0. Now for g of x, or part b, g of x equals x squared minus 2x plus 4 raised to 2/3 power. I don't have to do as much effort. We all don't have to do as much effort because I have that n that's odd, meaning I'm working with a cube root. Therefore, it's continuous. So because we have an odd root, n equals 3, the function g of x is continuous for all x. And this is because, again, for our theorem right above, we have a continuity rules that apply to roots, meaning a denominator, exponent denominator, or a radical, depends on your perspective, right? All right, continuity for trig functions. The functions sine of x, cosine of x, tangent of x, cotangent of x, secant of x, and cosecant of x are all continuous at all points of their domains. So let's take a look at our next example. Evaluate the limit as x approaching 0 of cosine squared x minus 1 divided by cosine of x minus 1. All right, so before starting, we see that we can simplify our numerator. We can factor it, right? Think of differences of squares. So my numerator can be written as cosine of x plus 1 and cosine of x minus 1. So I can simplify it. I have cosine of x minus 1 times cosine of x plus 1 divided by cosine of x minus 1. We see that we can simplify our function so that we have, and then we can apply the limit to the limit as x approaching 0 of just cosine of x plus 1. All right, well, cosine of x at 0 is 0. Oh, it's 1. Sorry about that. Cosine at 0 plus 1. Cosine at 0 is 1, and so we're left with 1 plus 1. We get 2. Intermediate value theorem. Suppose f is continuous on an interval ab, and L is a number strictly between f of a and f of b. Then there exists at least one number c in AB satisfying f of c equals L. So this is a more loose definition than what you might have seen in your algebra course. So what we're saying is that we have an a and a b, and if we have our function, if there is some line L, then there exists one number c. Let's do an example. Use the intermediate value theorem to show that the following equations have a solution on the given interval. So a solution means that I have an x-intercept, a value for x. So according to my intermediate value theorem, I just need to show that I cross my x-axis. All right, so I'm testing the numbers 1 and 5. If I test 1, or negative 1, let's go ahead and plug it in. I have negative 1 cubed minus 5 times negative 1 squared plus 2 times negative 1. That gives us negative 1 minus 5. Oh, just kidding. I need to move over the 1. So I move the 1 over. I have x cubed minus 5x squared plus 2x plus 1 equals 0. All right, now I can go ahead and test them. So let's test negative 1. I get negative 1 cubed minus 5 times negative 1 squared plus 2 times negative 1 plus 1. And we get negative 1 minus 5 minus 2 plus 1. We get negative 7. Let's go ahead and test 5. We get 5 cubed minus 5 times 5 squared plus 2 times 5 plus 1, which gives us 125 minus 5 times 25 plus 10 plus 1, which is 125 minus 125 plus 10 plus 1, we get 11. So is there a solution between our interval of negative 1 and 5? Well, yeah, because if we graph it, we have our points at negative 1, negative 7. So negative 1, let's say negative 7 is right here. And I have the number 5 and 1. 5 and 1, so say here. So that means if it's continuous, I somehow have a C which produces a solution, which crossed my x-intercept. I'm sorry, my x-axis. In other words, if we're looking for zeros or a solution, it's enough to say that one is positive, one is negative. They're different signs. But we have to be very careful for what it's asking. For this one, it was a solution. So we would be looking for it crossing our x-intercept axis. We're looking for an x-intercept. All right, that was 2.6 continuity. Thank you.